Have you ever seen this mysterious notation? I hope it does not scare you, but it did scare me. So what is it actually? They are bracket notation. Where does the name come from? It comes from the mathematical inner product. Someone added a vertical bar in place of the comma. Does it not look like something inside the bracket? For unknown reasons, the letter C is gone, and we have got bra and ket. Ket is the one with the right angle parenthesis, meanwhile bra is the one with the left angle parenthesis. What role do they fulfill? The ket is used to denote quantum states in general. Bra is the hermitian conjugate of the ket. And what about the shaping ket in the thumbnail? We will get to that later. Let us first learn how to use the ket properly. I am going to use the wave function of the harmonic oscillator. Remember that Q is just a change of variable. Here, N is the energy level of the harmonic oscillator. Using the ket notation, we can denote the wave function as ket psi sub n. If n is to take non-negative integer values, then we can write ket psi for each value of n. But what really matters here is the energy level. The good thing about ket is that you can put anything inside it. What is inside the ket is just a symbol. Now, to represent the quantum state corresponding to each energy level, it is enough to write the integer number n inside the ket. Therefore, we can replace the previous notation with ket 0, ket 1, ket 2, ket 3, and so on. This is the advantage of using bracket notation. You have a concise way to write a quantum state. You can put any symbol inside a ket or bra. If necessary, you can put a cat inside it. A chicken, swan, or steak will also do. That's, of course, if the cat, chicken, or whatever it is are related to a quantum state. Other examples include putting arrow inside the cat, or plus or minus. These notations are usually useful to denote spin states. Take a look at the blue tray. Suppose we have several possible solutions from n equals 0 to n equals capital N. We can write their superposition the lengthy way or the concise way by using the ket notation. Here, k sub n is the quote-unquote weighting coefficient for each state. Like the wave function, it must be normalized. In general, absolute kn squared is the probability of getting the state ket n from a measurement. If we want to do inner product between two states, the bracket notation also comes in handy. How about a more general quantum state? Here, ket alpha is a column vector whose components are complex functions. Bra alpha is the transpose, a row vector whose each component is equal to the complex conjugate of each function. How to calculate the inner product of the state ket alpha with itself? We multiply the row vector with the column vector, and do not forget the integration because each element is a function. What we will have is the summation of each integration from n equals 1 to n equals capital N. I want to demonstrate orthonormality in bracket notation by using the harmonic oscillator as an example. How do we do this? First, we express the inner product in integral form. Let us take the case where m is not equal to m. If m is an even number, then n is odd. Psi m is an even function, while psi n is an odd function. When an odd function is multiplied with an even function, the result is an odd function, which becomes the integrand. The integration of odd function across symmetric interval is 0. A different case happens when m is equal to n. An odd function multiplied with odd function is an even function. An even function multiplied with even function is an even function. Thus, the integrand is an even function, and the integration is equal to 1. This can be written concisely as Bra-M times Ket n equals to Kronecker delta. Bra and Ket can also be used to show completeness of a set of basis vectors. Each orthonormal basis can be denoted by Ket psi n. For this example, n takes positive integer values. A set of basis vectors is complete if this property is fulfilled. I am not explaining the proof of this proposition because it's pretty long. This kind of product, where Ket is put before the bra, is called the dyadic product or outer product. This concept is best illustrated by using column vector as basis state. Let us use 3 basis vectors. We calculate the outer product corresponding to each basis vector, psi1, psi2, and psi3. The result is 3 matrices. Add those matrices, and we obtain the identity matrix. Thus, we can say that this set of basis vectors is complete. Alright, this is the end of this tutorial video. I hope you find it useful. To support us to make better videos, don't forget to click that subscribe button. Thank you, and see you in the next video.